Hi. I'm so sorry it's taken so long for me to get these notes to you, but as soon as I got the first ones written, I wanted to record it, send it to you. I'm going to write that second set today, record it, even if it's this evening, send it to you. And then I'm going to have tomorrow's for you also. Regular class Thursday with Irene. Make sure you're doing this homework. I am going to get to WebAssign tonight. I can actually get up and get to my computer now with regularity, just not with any particular timing. It takes me a few more minutes to get things done these days. Enough about me. Let's get you some knowledge. Okay, so section 7.2. I guess I'm going to be pointing like this. I don't want to point like this, so let me turn it off. There we go. Yeah, I totally wasn't prepared. Here we go. So, it's like regular class. Section 7.2, we're still talking about systems of equations. We're still talking about two variable linear systems this time. In 7.1, which we talked about before the break, we were looking at nonlinear systems as well. We might have higher powers on our variables, so we might have multiple points of intersection. In this section, we're only doing linear equations, equations that have graphs that are lines. And we're going to use the method of elimination. To use the method of elimination to solve a system of two linear equations in x and y, we're going to perform the following steps. And since they're steps, we're going to go in order. First, obtain coefficients for x or y that differ only in sign by multiplying all terms of one or both equations by suitably chosen constants. Okay, so we want coefficients that obtain only that differ only in sign. So same number, one's positive, one's negative. Second step, add the equations to eliminate one variable. Doesn't matter which one. I'll show you which one I choose normally. Once we have eliminated one variable, we have an equation that is only in one variable, and we could solve it. And then we could back substitute it and always check our answers. It's the bonus of math, as we know we're right before we move on. So here are the operations that can be performed. First, we could interchange any two rows, and we're not going to interchange these rows very often, but it's a possibility. We can multiply an equation by a non-zero constant, and that's exactly what we're going to do in all of these problems, actually. And we can add a multiple of one equation to any other equation in the system. All right, here we go. So first we have this system, 2x minus 4y equals negative 7, and 5x plus y equals negative 1. Now, I already have y values that are different in sign, so what I want to do is I want to multiply appropriately so that they'll have the same coefficient. This is a minus 4y. I want to see if I can make this a positive 4y. To do that, I'm going to multiply this entire second equation by 4. So I leave the first one alone, 2x minus 4y equals negative 7. Multiply the second equation by 4, because all I really care about is getting a 4y here. But I have to multiply everything. That's 4 times 5x. That's times, that's a variable. I apologize that they look identical. 4 times 5x is 20x. 4 times y is positive 4y. And 4 times a negative 1 is a negative 4. Now that I've multiplied my second equation so that the coefficients of y are both 4, one's a negative, one's a positive, I can add straight down. 2x plus 20x is 22x. Negative 4y and 4y cancel out. They are eliminated. That's the whole goal of the process. A negative 7 and a negative 4 make a negative 11. And if we have 22x equals negative 11, we'll divide both sides by 22 to get x equals negative 1/2. All right, so in blue is my first step. It's kind of obtain coefficients for y that are the same, 4, differing only in sign. And then we added them, and then we solved them. So that's actually steps 1 through 3 right here in blue. Now I'll pick either equation. I decided to go with the one we didn't change. 2x minus 4y equals negative 7 instead of x. I'll use the negative 1/2 that we found. This is our back substitute step. 2 times a negative 1/2 is a negative 1. Minus 4y equals negative 7. Add 1 to both sides. Negative 7 plus 1 is negative 6. Negative 4y equals negative 6. So when I divide both sides by a negative 4, two negatives make a positive. 6 divided by 4 is the same as 3 divided by 2, and I have my answer. Don't forget this last step. That's what separates us from the social sciences. We could check this. So we check it, put 1/2 in for x, put 3/2 in for y. This time, since I used the first equation to find y, I'll use the second equation to check, and it works out. If it works out, I'm keeping it. That's my answer. Excellent. All right. Second system. 5x plus 3y equals 9, and 2x minus 4y equals 14. All right, so the y's, again, already have opposite sign. Wow, didn't know I did that. Y's have opposite sign, so I want to make them both the same. This one's a 3, this one's a 4. What could I do? How about we make it easy? Let's make them both 12. Right? I can multiply this top equation by 4, and 4 times 3y will be 12y. Multiply the bottom equation by 3, and 3 times negative 4 will be negative 12y. I'll have a positive 12y, negative 12y. That's what I'm going to do. So I choose to eliminate the variable that already has opposite signs. Almost always, I've found. So we'll see in a couple more examples. So I multiply the first equation by 4. 4 times 5x, 4 times 3y, 4 times 9. I multiply the second equation by 3. 3 times 2x, 3 times a minus 4y, and 3 times 14. Remember, our goal was to get coefficients of y have the same value but opposite sign. I chose them because they already had opposite sign, so I found the first thing that I can make 3 and 4 both turn into. When we add straight down, 20x and 6x is 26x. My 12s are eliminated. I won't do that again. I know it's horrible. 36 and 42 is 78, and when I divide 78 by 26, I get x equals 3. Choose either equation. I went with the top one, 5x plus 3y equals 9. Instead of using x, I'll call it 3 because that's what we found it to be. So 15 plus 3y equals 9. Subtract 15 from both sides. 9 minus 15 is a negative 6. If 3y equals negative 6, we'll divide by 3 and get y equals negative 2. Since I used the 5x equation to find y, I'll use the 2x equation to check. Is 2 times 3 minus 4 times negative 2 equal to 14? That's 6. That's plus 8. 6 and 8 definitely make 14. We have a good answer. All right. So each time, make the coefficient of one of the variables the same in number, opposite in sign. It doesn't matter. These ones have just been y. That's why I went with them first. But here I see minus 2x plus 4y equals 1, and a positive x minus 2y equals a negative 1/2. The x's and y's are both opposite sign already, so let's just eliminate x's. This is a negative 2x, so I need a positive 2x. To do that, I'll multiply the second equation by 2. I'll leave the first equation alone, negative 2x plus 4y equals 1, and then 2 times x minus 2y equals a negative 1/2. Multiplies to give me 2x minus 4y, and 2 times a negative 1/2 is a negative 1. When I add these straight down, I notice that both the x's cancel and the y's cancel or are eliminated, but also the 1 and minus 1 make 0. What I end up with is an equation 0 equals 0, which is always true. And if equation is always true, it doesn't matter what you pick for x, it's independent, the y will follow. So what we do, anytime we get a system that is always true, we'll solve the either equation for y. I chose the top one because there's no fractions already. So I took x minus 2y, no I didn't. I took the top equation, as I said, minus 2x plus 4y equals 1. I added 2x to the other side, and then I divided by 4. So y is equal to 2x plus 1 over 4. So this is always true. Whatever solves the first equation will also solve the second equation. So for any x you give me, I know the y has to be in the form 2x plus 1 divided by 4. All right, so it's always true There's an infinite number of answers, and that's why it's in variable form. There's no one single answer, and we're going to look at a visual of that in just a minute. All right, so sometimes we'll get an equation that's always true. Let's look at the next one. D, 8/5 x plus 6/5 y equals 4. 8x plus 6y equals 3. Now, everything's positive, all positive coefficients here, so I need to change one of them to negative. If I have to switch one of them to negative by multiplying, how about I multiply the fraction one and get rid of denominators at the same time? Let's make these both 8, but we'll make that top one a negative 8 by multiplying by a negative 5. Cancel the denominator, cancels denominator, and so on. So when I multiply negative 5 times 8/5 x, the 5's cancel, and I'll have a negative 8x. When I multiply negative 5 times a 6/5 y, the 5's cancel, and I'm left with the negative 6y. When I multiply negative 5 times 4, I multiply to get negative 20. Finally, no fraction. I'm going to leave that second equation alone. It doesn't have any fractions. My 8's are the same number, opposite sign. So when I add them straight down, my x's are eliminated, and I notice my y's get eliminated as well. However, unlike this one, when I add on the right-hand side, I don't get 0. I get 0 equals negative 17. And it's not true, right? 0 is never equal to negative 17. It's never true, so we'll have no solution. Okay, so we either find a solution where we have x equals y equals, or we'll find a solution where 0 equals 0, in which case we put it in terms of variables, or we'll get a nonsense equation, 0 equals any other number, which is never true and no solution. 3 types of answers in this set of homework, all right? Different systems we're looking at. Previously, I've told you, let's just get rid of the fractions. Let's just get rid of the decimals. And I know some of you really don't need that. I wouldn't call it a crutch necessarily, but maybe it's an unnecessary step. So let's do this one and just deal with the decimals. All right, we got this. As I look at system E, I see that my y values have opposite signs. So I need to figure out what to multiply 0.5 by and 0.4 by so I could get them to be the same number. Well, it's kind of like 5 and 4, not kind of like, it's a 5 and a 4. So let's use 4 and a 5, right? 4 times 5, 5 times 4, should get the same answer. Let's check it out. 4 times 0.2x is 0.8x. 4 times a negative half is a negative 2y. And 4 times 27.8, negative 27.8 is a negative 111.2. I know it's negative 111.2 because I had to do that 4 times just to figure out where I made my mistake. It was there. So my y is negative in the top equation. My y is positive in the bottom equation. Let's multiply, make them the same value. 5 times 0.3 is 1.5x. 5 times 0.4 is 2, right? If you have 40 cents 5 times, you got $2. 68.7 times 5 is 343.5. When we add 0.8x and 1.5x, we get 2.3x. My y's, positive and negative 2, are eliminated. That was our goal. And when we add the right-hand side, we get 232.3. Dividing both sides by 2.3, we get x equals 10.1. And I checked that several times as well. It didn't sit well with me, but I have decimals here. Makes sense I could have decimals here. Now that I have x equals 10.1, I could go back in and substitute. Either equation doesn't matter. I seem to be in the habit of taking this top equation. So I have 0.2 times my x value, 10.1, minus 0.5y equals negative 27.8. I always use the original equation, never one of these multiplied ones, just because I make mistakes here. And if I use the original, there's less chance for me to replicate errors. 10.1 times 0.2 is 2.02. minus 0.5y equals a negative 27.8. If I subtract 2.02 from both sides, I'll get a negative 1/2 y equals a negative 29.82. And when I divide, I'll end up with y equals 59.64. We could check this one on Desmos if we would like to, mostly because I didn't want to write down all the decimals to check it right here. Yeah, I'm going to claim lazy on this one, but don't worry, I've got the next one. Every single time, it's the same. Oh, look, they're already opposite sign. Let's find a way to make them the same coefficient. We can multiply by any non-zero number, positive or negative, if we need to change the sign. All right. So let's talk more about these systems, or these systems. It is possible for a general system of equations to have exactly one solution, two or more solutions, or no solution. And by two or more solutions, we actually have infinite solutions. Well, this is in general, okay, in general. But if we limit it to a linear equation, if a linear equation has two different solutions, it must have an infinite number of solutions. So we won't have like a line intersecting a parabola like we did in 7.1. We'll just have two lines intersecting, and it happens never, once, or always. Okay? Exactly one solution. Our points will intersect in one point, and the slopes of the two lines are not equal, right? They don't have the same tilt. If we have infinitely many solutions, remember that was 0 equals 0, the two lines will coincide, right? So they're the identical graph. The slopes of the two lines are equal, but so is the y-intercept. If we have a no solution, which we did above, that means the two lines are parallel, and the slopes of the lines are equal, but they have different y-intercepts. Okay, some more terminology for the drop-down menu questions. A system of linear equations is consistent if it has at least one solution. So let's use orange-ish. What is that, yellow? I don't know. These ones are consistent because they have at least one solution. If it is inconsistent, it has no solution. All right, so circle. A consistent system with exactly one solution is independent. Independent has exactly one solution. It'll look like this. We have an answer. All right. Otherwise, it's dependent. And we saw that dependent one, slow scroll, not so slow. Our dependent one is the y value depends on the x you choose. All right, so we saw that as well. Coming back down, we're going to match each system of linear equations with its graph. So what I did is I took A and I said, all right, let's eliminate this x. I multiplied the top equation by 2. So I'll have 4x minus 6y equals 6. I just did the first step and I got 0 equals 12. That's never true, so they will never meet. Graph 2 goes to part A. I took the next system, 2x minus 3y equals 3. I just multiplied this bottom equation by a negative 2. That way I only had to multiply one equation and not both. When I multiply through by a negative 2 in the second equation, I'll have a negative 2x minus 4y and a negative 10. Notice x is eliminated, but y is not. As long as I still have a variable remaining, I'll have an intersection. I'll be able to find an answer. All right? If the variable's canceled out and it's a nonsense equation, they never meet. If the variable does not cancel out, we know they meet. Third equation, I multiplied this top by 2. Right? Top equation by 2. I got 4x minus 6y equals 6. And I got 0 equals 0, which is always true. So they have to be the same line. The first step is going to tell you exactly what type of system you're going to have. Is it consistent? Does it have an answer? If it is consistent, does it have one answer or infinitely many? Or is it just inconsistent with no solution? All right. Excuse me. Last question. An airplane flying into a headwind travels the 2,000-mile flying distance between Chicopee, Massachusetts, and Salt Lake City, Utah, in 4 hours and 24 minutes. On the return flight, the same distance, 2,000 miles, is traveled in 4 hours, because the wind helps you a little bit when you're going from west to east. Find the airspeed of the plane and the speed of the wind, assuming that both remain constant. Okay, so from Massachusetts to Utah, it's 2,000 miles in 4 hours and 24 minutes. Keep in mind that 24 minutes is 24/60ths of an hour. 24 divided by 60, 6 goes into both of them. 4/10ths. 4/10ths of an hour, so that's 4 hours and 4/10ths, 4.4 hours. You're finished in Utah, you've checked out the Mormon Tabernacle, and it's so beautiful, it's incredible. Found your way around, had a great time, you're headed back to Massachusetts, still 2,000 miles, but this time you make it in 4 hours. Okay, so we have our information, let's figure out what we know. We know distance equals rate times time, right? If I go 60 for 2 hours, 60 miles per hour, for 2 hours, I've traveled 120 miles. So I know both distances are equal. I need to find the airspeed of the plane and the speed of the wind. So let's define those here. Let P be the speed of the plane and W be the speed of the wind. I like for it to be clear. X and Y tells me nothing. So what I know is the distance, 2,000, is equal to the rate of the plane minus the headwind, right? The wind's blowing in your face and slowing you down against the wind in 4.4 hours. So 4.4 times P minus W. Coming back, Utah to Massachusetts, the same 2,000 miles. This time, the plane and the wind are traveling in the same direction. So they're working together. And it only takes 4 hours. Distance equals rate times time. So this is how we think of it. Let's write those out. I multiplied by 4.4 through, and I multiplied the second equation by 4. So now I have my two equations. 2,000 equals 4.4p minus 4.4w. And 2,000 equals 4p plus 4w. Somehow this is all going to work out. So what I decided to do is eliminate P. I don't know why, I just did. To eliminate P, I'm going to multiply by -4 in my top equation. So -4 times 4.4. I'm going to multiply by 4.4 in my bottom equation. So I'll still have 4 times 4.4, both places. Top one will be negative, bottom one will be positive. 2,000 times -4. 4.4 times a -4, and -4.4 times a -4. Second one, 2,000 times 4.4, 4p times 4.4, and 4w times 4.4 give us our equations over here. Woo! So I multiplied by a negative, so positive, positive, negative becomes negative, negative, positive. In the second equation, I multiplied through by a positive, so everything stayed positive. The negative 8,000 and a positive 8,800 add to give me 800. The p's are eliminated. That's exactly what I wanted. 17.6w plus 16w is 33.6w. And when I divide 800 by 33.6, I get 23.8 as the speed of my wind. And I'll be honest, I don't like that. I mean, wind doesn't just fly in actual miles per hour. There's decimal, right? And depending on how fine-tuned we measure our stuff. But I didn't really like that. So I did it again. And I used the same set of equations. And this time I eliminated W. All right, so if I eliminate W, already has opposite signs. I should have went with that in the first place. This one, right, already have opposite signs. There I go. When I multiply by 4, I multiply by 4.4. It's the same thing. The only thing that's changed here is I didn't multiply by the negative sign in the top. So it's a positive 8,000, a positive 17.6p, and a negative 17.6w, because these w's are going to cancel out. 8,000 plus 8,800 is 16,800. 17.6p plus 17.6p is 35.2p. And when I divide both sides by 35.2, I get 477.3 as the speed of the plane. And this is miles per hour. And I thought to myself, that doesn't seem right. So I thought I'd check it on Desmos. And look at that. If 2,000 is 4.4 hours of the plane working against the wind, and 2,000 is 4 hours with the plane working with the wind, that is exactly what my answer is. 477.3, 22.7 for our speed of our wind. Check it again. 22.7. I missed something here. I didn't even notice it. I'm going to check that, see where my error is. Good thing I checked on Desmos. I checked it on Desmos before recording and didn't even notice that it wasn't the same. Sounds like my dogs want to say hi. Must be time for me to check out. I'm going to go write the notes for 7.3. I'm going to record it this evening and send it on to you. I'll be there soon. I really hope. I'll be answering web assignments soon. Thank you for your patience and continued dedication to your math learning.